Hi, I'm Catherine Porter. I'm an independent energy consultant, and in today's video we're going to talk about balancing. Now, what is this balancing thing that we hear about in the electricity grid? Why does it matter, and why does it get more expensive when we start putting renewables on the grid? So I've spoken before about how we have an alternating current grid with a frequency of 50 hertz. So to recap, we generate electricity by rotating one magnet inside the magnetic field of another magnet. This creates current and voltage, which vary in a nice wave shape, a sine wave shape. And the speed at which that varies is known as the grid frequency. We rotate our turbines in conventional gas, hydro, nuclear power stations at 3,000 revolutions per minute, or some multiple of that. And that generates a current and voltage that varies with 50 cycles per second, or 50 hertz. Now, the National Energy System Operator, NESO, which operates the electricity grid, is required by law to keep the grid frequency at 50 hertz plus or minus 1%. And the reason for this is that electrical equipment is extremely sensitive to frequency. If it deviates away from an operational tolerance, it will simply turn itself off because it will need to protect itself from damage. So that's be power stations, substations, machines in factories, all of these things, they can't tolerate grid frequency deviating away from that 50 hertz plus or minus 1% by very much. The 1% gives some margin for error, but not very much, and that's the standard to which grid equipment is expected to operate. So this frequency is also linked to supply and demand. If you have more demand on the grid, so more consumers trying to use electricity, then you have power stations generating electricity, then you will have a reduction in the frequency. It will tend to try and actually slow down your turbines. And the opposite is also true. If you put more electricity in than people can use, that will try and speed up the frequency. It's a little bit analogous to water in a pipe. If you push more water into a pipe than you take out of it, then eventually the pressure inside the pipe builds up and the pipe will burst. And similarly, if you don't put enough in and you're trying to take more out, then you just won't have enough water left in the pipe. And so effectively your pipe system won't work properly. And our electricity grid is similar to that. So you have to keep this frequency inside 50 hertz plus or minus 1%. Now, there are various things that can cause that to change. And if you think about a conventional power grid where you've got lots of, a relatively small number of large power stations, gas, nuclear, hydro, historically we had coal and oil as well. And they all do their thing. And, occasionally equipment breaks, machines always break. So sometimes one will suddenly just vanish off the grid. And also they can have some small variations in output based on the weather and other factors. In very hot weather, you would see a gas power station maybe having about 5% less output than it would on a day with a more normal temperature. So you get these variations in generation. But typically, your variations on the demand side are bigger. First of all, you have no immediate visibility on demand. Most users of electricity aren't connected to the high voltage transmission system, which is what NESO is operating anyway. So NESO can't see these people, can't see their meters. They can only see the meter at the point where the low voltage network connects to the high voltage network. And so effectively you model what you think demand will be, and then you essentially categorize consumers into different categories, and you have assumptions about their consumption based on the weather and other factors that you then use. So we would have things like, is there a big event going on? Is there a big sporting event? Lots of people will watch that sporting event, but then when it finishes, they're all going to go and make a cup of tea and visit the bathroom. So you're going to have lots of kettles going on, lots of fridges opening, lots of water pumps running. And then quite a significant instantaneous spike in demand, or a spike that's spread over a few minutes, but in a relatively constrained amount of time. And if you didn't manage that, if you didn't anticipate it, then your frequency would fall and you would risk stuff disconnecting, and the ultimate consequence of that would be a blackout. So historically, the whole attention has really been on the demand side. How do we forecast our expectations of electricity consumption to make sure that we have enough generation available? And so we have something called the balancing mechanism. And in this mechanism, NESO says to all of the participants in the high voltage grid, so whether that's power stations adding electricity into the grid, or suppliers or large industrial users trying to take it out of the grid, either into their factory or, in the case of suppliers, into the low voltage network, so they can then move that on into consumer premises. They all have to tell NESO their intentions by what we call gate closure, which is 1 hour before the start of the half-hourly delivery period. So we divide up our electricity market into half-hourly chunks, and these are what we call settlement periods for the accounting process for the whole of the grid. But NESO has to balance everything in real time, minute to minute, second to second, at every point of the grid. So all our trading arrangements are essentially at the high voltage transmission system level, and it's essentially a virtual market that assumes that every point in that system is identical to every other point. So what happens is that by gate closure, this 1 hour before delivery, every market participant has to say to NESO what they're going to do, how much of their electricity they're going to put in, how much they're going to take out. And everybody's supposed to run a balanced position. So if I'm a power station and I expect to generate 750 megawatts at 5 p.m, then I say, I do that. I say I'm generating 750 megawatts at 5 p.m, but I can't just leave it like that. I can't just generate the electricity and put it in the grid and then say, well, use it if you want. Somebody has to buy it, so because the grid has to balance. So you would sell that electricity to somebody else, and let's say you sell it to a supplier who has customers that they're going to take it to. So now you, as the power station, you have a balanced position. You're going to put in 750 megawatts, and the supplier is going to take it off you, and that gives you a balanced position. Now, the supplier's position looks like, well, I've bought 750 megawatts from this power station, so I need to take that out of the transmission system into the distribution system, and that will mean that I have a balanced position in my energy account on the transmission system. And so everybody does this. Everyone says, right, how much they're putting in, how much they're taking out, either by generating and selling it, or by buying it and taking it over to consumers. And then when you come into real time, NESO says, okay, well, overall, the whole market looks pretty balanced, but actually we need more electricity in the south than we've got in that region at the moment, and we actually have too much in the north. So what they might do then is, because of constraints on the grid and that you can't move all the electricity that you need from the north to the south, would be they'll turn off some generation in the north and turn on some generation in the south. So they make all of these adjustments, and also they have tools in place, reserve products, so if something does break suddenly, they can respond to that. So you have batteries that can respond instantaneously, and they actually just do it automatically. They see the frequency, and if it's going to certain trigger levels, they'll just respond by injecting electricity. And then NESO will instruct, say, pumped hydro that can respond in 16 seconds. So it has all of these tools in place that can respond if something breaks or something unexpected happens. If there's suddenly an unexpected increase in demand because it turned out to be a bit colder than you expected, whatever it might be, they have the tools to cover that. So, and as I said before, you have these variations. So particularly with suppliers, they're effectively guessing what their actual amount of electricity they take off the grid will be. And so each half-hourly period, you look at what people said, and they said, oh, well, we're going to have a balanced position. But actually in practice, they never do, right? So there's always small variations. your power station actually didn't generate 750 megawatts, it generated 747, and your supplier thought it was going to take 750 megawatts, but actually consumers used a little bit more than expected and they took 752, and that 5 megawatt difference, NESO has to make that up, and it will do that by asking some other power stations to turn up or use some batteries or some other tools, but then that has to be paid for. And so they pay the money to that provider of that, we call it a balancing service, and they will charge money to the suppliers and the generators or whoever it was that didn't actually have a balanced position at the end of the day. But that doesn't quite cover all of the costs. And so the residual cost from that is then charged through to consumers as part of balancing costs. And this is a very established way the market works. In fact, when every market participant is informing NESO about their intended actions, they also provide what we call a bid and offer ladder, which sets out the amount of flexibility they have to change their position. So when NESO is trying to manage the grid constraints and other issues on the network, it will ask people to turn up and turn down, and that's not to do with them not having a balanced position. That's to do with overall grid management, and those costs end up on the consumer bill. And so we have this fairly complicated system where everyone says, okay, so I'm a gas power station. I told you I was going to generate 750 megawatts. Actually, I could generate anything between 350 and 750 megawatts. So if you need me to turn down a little bit, this is the cost implication for that. And normally what happens is that the generator would be willing to pay some money to reduce their output because they save some fuel cost. And then similarly, if you've got somebody saying, well, I'm only really expecting to run at half load today, if you want me to increase above half load, that's going to cost you. And obviously then they have to, that's money that they need to receive because they incur additional costs from increasing their output. And so this is how the balancing mechanism works. Every half an hour, NESO is doing all of these actions to make sure that the grid is balanced everywhere at all points in time and in space. So why then do renewables make this more complicated? Well, as I explained before, in a conventional grid, your main source of uncertainty is on the demand side. You don't really have visibility of what consumers are doing in real time. You can only estimate what they're going to do. And so that introduces quite a bit of uncertainty that you have to manage when you're keeping your supply and demand closely matched so that you can keep your frequency at 50 hertz plus or minus 1%. Now that if you now introduce renewables, you're bringing a similar level of variability onto your generation side. And a lot of these renewables are also connected to the distribution network. So a renewable generator connected to the distribution network looks like negative demand. So it acts to reduce demand on the transmission system. So if that generator breaks, then that will just suddenly increase demand. Or if it turns off for whatever reason. We saw this in Spain. In the middle of the day when they had that blackout, a lot of solar power stations just turned off because prices went negative. But because these were connected to low voltage networks, to the system operator on the transmission system, the high voltage system, that just looked like an increase in demand because suddenly demand that was being met locally was no longer being met locally. Now it had to be met by the national transmission system. And then also you do have transmission system connected renewables like big wind farms, some big solar farms. And so now you're bringing this very fine variable generation source onto your grid. And that generation source is highly variable in real time. Gusts of wind and clouds impact how much they generate, and you can't predict that. So you can overall forecast, it's going to be a certain level of wind or sun on any given day, but you can't know at every point on the grid just exactly how many gusts of wind will happen at what point because wind speeds aren't constant. And so this makes the output of these generators really variable, and it creates a much bigger challenge for NESO to balance supply and demand in real time because they can't see that stuff coming. Now, obviously, they can see a big storm or a big lull. They're going to know that overall you're going to have X number of gigawatts at any one time. But second to second, you can get quite a lot of variability in that has to be managed. If you suddenly have some big gusts of wind, or some cloud passes over a big solar farm. You see this in Australia. You can actually track clouds on the satellite and see how that impacts generation output. And it can be quite significant. So this feeds into your grid in real time. And it's highly challenging to manage that, because now you've got a load of variability on the demand side that you always had, and a really huge amount of variability on the generation side that you didn't used to have. And that's happening all over the grid where you've got renewables connected. And even worse, you can't necessarily see it because it's on the low voltage network, or some of it's on the low voltage network. And you just have to react to the impacts that it has because you can't necessarily plan for it. So obviously that makes it harder. Harder equals more expensive. The system operator has to make a lot more of these balancing instructions to different types of assets, constantly fine-tuning what people are doing. Obviously they're using batteries a lot for this, because batteries can respond instantaneously, but for bigger differences they need to do more substantial actions. Now, if you take big storms, for example, they're a huge risk because wind turbines will have a shut-off, an automatic shut-off when wind speeds go above a certain level. And so on a stormy day, you don't know at what point the wind speed will reach that level and will cause all these turbines to turn off. And so sometimes what happens then is NESO has to do what they call anticipatory curtailment. So they'll look at the wind estate and they'll say, well, we think that wind farms in that particular area are going to be vulnerable to this shut-off. And it happens instantaneously. So one minute you've got some gigawatts and the next minute you don't. And that would obviously cause a massive drop in frequency. So sometimes they'll just tell them, well, you've got to turn off because we can't take that risk that you suddenly just disappear off the grid. It will be too dangerous. And then the other thing they can do is they can put gas power stations in what we call spinning reserve. So they're running up to speed, ready to synchronize with the grid at any moment. But they're not actually generating electricity. And so, but because they're up at speed, they can start injecting electricity into the grid really quickly. You don't have to wait for them to ramp up. They're already ramped up. But obviously this it actually uses almost as much gas as when they generate. So it's a pretty expensive way of managing that type of risk. But in big storms, that's what happens. NESO will do some portion of the risk they'll cover with anticipatory curtailment, and other portions of the risk they will cover with gas plant in spinning reserve, so that they can get that fast response that they need if they need it. And of course, all of that costs money. If you're asking gas power stations to spin its turbines up at speed for, it could be hours in case the storm causes wind farms to turn off because of high wind speeds, then that costs money and that has to be paid for. And those costs get added onto bills. It feeds through into the network cost portion of the bill. And these costs are right now about a couple of £1 billion a year. They're expected to grow, and they have come down a little bit since 2022 because they are linked with gas prices. So because obviously if you're running your gas power station in spinning reserve, you're paying the cost of that gas. So we did see some decline because of the decline in gas prices, but the underlying trend is for these balancing costs to go up. And the more we put renewables on the grid and the more we replace conventional generation with renewables, the less secure the grid will be, the more variable it'll be. You'll have variability on both the demand and the supply side. That's not necessarily acting in a complementary way. And this will make balancing harder and more expensive. And so I hope that explains how our balancing system works in sort of high level terms. I hope you enjoyed this video, and I'll see you in the next one. Bye.